back to day 2. Hope you're still fully energized. We laid yesterday some foundations on robotics, and we laid a bit of the ground to talk about more interesting stuff hopefully today. So I'm going to talk much more about long-term autonomy in what we can call changing spaces. So the word long-term and time will come into the focus a bit more today. The challenges and the opportunities that come from that in the context of quite a number of different projects. I suspect nobody has really had a chance to do the homework I said. Has anyone tried to run this Docker container? It's fine if you say no. I didn't expect it. There's always so much social program going on, so it's still available afterwards. You can have a play with that. I was muted. Excellent.
Does that work better? Right, cool. Yeah. They all said so. It must be good. So what I did for you was we had this little robot in a vineyard yesterday, and I showed, as part of the homework, you could try different SLAM methods, different maps, to create different maps of that environment. And what I've done now is I've basically changed the time of the year, because that's something that we are really interested in. While when I created the map, which in the end looked like, where is it? Put it here. So this was a 2D LiDAR-based map, quite simple one. It looked like this, and that was created when the plants were just developing very early on. So like something in March or so, right? Simulated in this case. So we can simulate them at different growth stages, and you can have a play with that. And then now, of course, they have massively grown, and that's a common problem, right? If we have created a map at some time, it may become outdated. So now these crops have grown, and I'm going to show you a little bit what this means. So when we look here, this is the, again, we've developed this in ROS, and this is the visualization. It shows the robot's internal state. And we see the red dots here are the dots that are kind of flickering are the current LiDAR readings. And you can already tell from just looking at them that they don't quite align with the map. Right? The map was created like 2 months ago, and now actually the plants have changed quite significantly. What hasn't changed is the wall at the top, but no LiDARs are hitting that wall at the moment because they are nicely occluded by the overwhelming canopy of the crops that have developed. So this is a challenge, right? If that is where we have the map we've got, and now we want to localize in it, we can try it out, right? And here we see at the moment these sort of small arrows that you can probably not really see, but if I zoom in, you see these are all tiny arrows, and they represent these particles. Talked a little bit about particle filter being one of the state estimation methods that people use, and you heard Cyril talking about one of those as well. So each of these little arrows is a hypothesis where the robot is, right? And that we've just started this as an initialization. And the whole point of localization is comparing your observations to the map and then finding the most likely a posteriori distribution, let's say, from what's the most likely position that I'm at. So I'm going to continuously track these multiple hypotheses, giving more weight to those that match the observation well, while basically getting rid of those that are not matching the observation very well. So in this case, I've even launched a little bit of a robot navigation system, so I can actually, rather than manually controlling it, I can tell it to go here. And it will plan a path, and you can probably just about make out that it made a little green line there. I don't know how well you can see it, or you can just about make it out there, right? And that's the path the road has planned using this sort of shaded obstacle map, so it kind of tries to stay away from these plants. You see the readings don't match up so well, and we already see one of other interesting fact that is happening. This distribution, while it narrows, right, all these particles narrow around the center, because we can probably say that we are somewhat in between those many obstacles. They also spread out in that direction because it's almost impossible from this very massive perceptual aliasing to know exactly where along the row we are. So this integrates the odometry, so the sort of, how much we are moving, we believe we're moving from our wheel spinning, and the LiDAR readings here. So it looks kind of all right. Not too bad. Ideally, you want all these particles to come together in one spot. They don't. And now it seems to have stopped. What we see here is exactly the typical problem we have in this situation. So I don't know if I can zoom in a little bit further. And look at this. Hang on. Normally zooming works. Yeah, you can just about see this now. So this is the plot of the ground truth, which is green, so that's where the robot actually is, versus the red line where it believes it is because of its perception. And we see they have diverged because we didn't quite match up with this sort of, we couldn't quite localize ourselves correctly in there. And what this resulted in was the robot believing it was in the wrong space and taking that turn too early. So it drove right into the crops at this place. Or well, it wants to drive into the crops, so it has, the obstacle avoidance kicked in and said, I can't really go this way. But the actual path it had planned isn't valid anymore. And that is because we are in the wrong place. We just kind of have mislocalized because indeed the map is no longer valid. Yeah? So that's a sort of bit motivation of this works, and that's something we can play around with. So, that said, and this is a video of that, what can we do when the world changes? And I'm going to tell you a number of different things how we are potentially tackling world change. One obvious option would be just kind of run SLAM all the time, but that's not a good option for instance in agriculture because you want to have the same map reference all the time. You want to actually map out crops and make sure that you can map them reliably as you go again and again and again. So this is some recent work that one of my PhD students did around learning long-term 3D stable objects in maps. So rather than, when you are doing the mapping, and you may be doing this mapping several times, right? That's something that some data sets that are long-term data sets, they are terribly sparse. There's not many people who have actually published long-term data sets. This is one example. So we've got one our own. That's from the simulation that you've just seen, where we've taken this into reality, and you see this at the top there. So that's one image from an actual vineyard in Greece, part of a European project. And here, this is from a data set that is a parking lot, or it's actually a campus of a university, where they drove around and gathered these 3D pointer clouds, and we point clouds from that, and when we've done some SLAM on there, integrated that, etc. So changes, of course, can be this detrimental to localization reliability and accuracy, as we've just seen in this very simple example. Things that may change. For instance, you may have mapped cars that are no longer there. They make fantastic features as long as they're present. The worst thing can happen, of course, if one car was there at one point and now it's in the separate bay. Right? The feature matching all of a sudden matches very well with that car, and you're easily like a car length off when you use that feature. So we want to know what are the things we can trust. In a way, that's quite closely related to semantic segmentation, right? We may want to actually classify what we see in the scan. So we may explicitly say cars are rubbish and we don't want to take them and don't want to integrate in the map. There's also a lot of work that people do, in particular autonomous driving areas, again, where they do moving object segmentation from these 3D point clouds. Again, that's very closely related. The main difference that we are interested in, they are mainly talking about short term, so we actually see the change happening, right? As another vehicle is moving, a pedestrian is moving. Here the problem is we've got very sparse observations. We don't see the thing changing. We just see the world at one state, and then later on it has changed. But we haven't had a chance while we are mapping to see that something is changing. Okay, so what we thought, what would be interesting to, rather than learning explicitly the objects that directly explicitly learn different types of objects, basically doing a semantic segmentation, we thought it would be more interesting to actually classify objects regarding their stability. On how this is done is basically taking a long-term data set where we have different time slices for the same environment, and then learn basically pretty much end-to-end a regression onto some stability feature, telling us something that looks a bit like this, has this sort of shape in our 3D world, is potentially stable. That might be something like posts, like lampposts tend to be stable, or tree trunks, while tree leaves are rubbish. And then basically learn it end-to-end and use it as a filter for our map to just only have the actual reliable features in it. So that general idea, relatively simple. We take the same environment, so we have mapped the same environment a couple of times. So this is map 0, 1, 2, 3, 4, whatever. And then we just do sort of associations, really point-based, basically something like ICP, iterative closest point, algorithms where we just see, all right, what's the minimum or maximum or median distance of every point to its other points in the same reference frame maps? Right? So some things that are stable, basically you will always find that the nearest point that matches it, the nearest data association is relatively small. It won't be that far away if it's a stable thing over several time slices. While something that has appeared in one map and disappeared in the other, of course, will probably have a quite long distance to a matching point, to an associated point. Yeah? And then we use this sort of point-based regression network to then do for every point effectively a metric of how stable that one is. So we don't have to really do any labeling. That's the whole key point here. We take these temporal data sets, and the labeling for this machine learning task comes from the long-term slices that we've got. Okay? So we use basically the multiple maps as the labeling to then train the individual networks or the individual maps onto that feature of the distance. So, you know, we take these raw observations, we filter some sort of ground removal out and do some denoising and stuff like that. Then we register them all with respect to the first map so that they are spatially correctly aligned. And then we have a bunch of maps that are nicely spatially aligned but have differences over time. We use this to calculate these sort of labels for those. So the distance, the median or minimum or maximum distance. Usually we take the maximum distance over the different maps for each of those points, and that provides us with the right labeling. So we have got principally then the labeled maps, and because we like things to be somewhat continuous, in an interval we use a function here to actually turn the distance into a value between 0 and 1 that characterizes how stable something is. Yeah. Good. So then we can train our network that's based on PointNet++. You could use almost any other backend. There's many different backends you can use for 3D point clouds these days. There's quite some interesting papers around that have proven that there's probably not that much of a performance difference in terms of actually accuracy, but there's many of them that have a similar comparative performance, bit of difference in computational efforts. So we used this one, and then we trained that. I'm not going to go into the exact details of this particular algorithm. Okay, so we've done this analysis on this North Campus long-term data set. So, you know, it's quite nice. It's collected over a 15-month period. We like that if it spans the whole year. So we've got a full season range in it, right? So that's good, because things tend to change a lot during an entire year when you go outdoors. And then we basically mapped out this for different areas. We took 2 areas here to compare, and then we just did the analysis of how well actually our accuracy works for this predictor, for this regression, comparing it to the ground truth. The ground truth in our case being this auto-labeled temporal label map. Good. And yeah, it actually works pretty well. So we've trained it on one map, on one area, let's say, so on all the temporal maps of this one area, and deployed it into the completely different other, and vice versa. And the generalization was pretty all right, I would say. So we've looked at a sort of simple baseline where we just done the actual difference between the original map, and it was just done ICP and see how well that worked. And that wasn't, you know, not in some cases it worked pretty all right, but in many others it not. And we've done this for different time slices. So the M0, 1, 2, 3, 4 is basically then, because you can take each map as the one that you use as the foundation map, let's call, and see the temporal differences. And what it does, so what is probably important to note here, so we trained this regression to identify typical objects effectively that turned out to be stable, right? So that means if you now go to another similar domain, like outside campus maps, public areas, etc., it will work reasonably well. But of course, you need to have trained this in similar environments, right? So we've done a good transfer here from completely distinct regions, but of course it has also cars in it, it has lampposts, and it has trees in it. So sort of domain is similar, but of course the exact space here is very different one. And we've done the same now also in agriculture, in these sort of vineyards, for instance, where you can see that the structures it infers as stable than are these sort of vertical poles, nice flat structures, walls, etc. And then you can use this to actually get better localization and get rid of the problems that we've seen early on in this little demonstration. Yeah, because you just have actually features that are stable. Now, this was based on a map system, so we've basically filtered the maps, so we got rid of the stuff that we deemed unstable, so that's just a kind of thresholding operation on the predicted stability of them, so you can play around with that a little bit. But the novel ideas, or the thing that's now going to come out hopefully at ECMR, is to basically apply it directly on the filter on this laser scan. So you filter directly the laser data out for things that actually you already know are probably carry very little information, right? And then you can also use weights instead of just thresholding and say we're going to remove those unstable points. You could also just say, well, we're going to give them a lower weight, a lower confidence in this area as well. You give higher weight to laser points that actually are likely to be linked to objects that are actually stable. So that's one way of basically using machine learning to identify long-term stable features. There's many different approaches, and we are currently working also with people in Bonn to use what is typically used to sort of moving object segmentation, where you are focusing on these sort of moving objects in short term, cars, people moving, etc., and basically take these approaches and see how well they fare in comparison for long-term data sets, where you basically compress all the time slices into a short-term time sequence. Good, so that's one way how to deal with dynamic structures. I'm going to talk a bit more now about another interesting observation when you look into the real world, right, in time. Our world is clearly not static. We've seen that. We know that. This is not just in outdoors environments. But what is interesting in particular about human inhabited spaces is it's full of periodicities. Right? We all have typical routines. We get up at a sort of certain time in the morning, then we have some food in regular intervals, and we go back to sleep. We have other sort of routines of like work days, weekends. Lots of the stuff we do actually is in that sense, while it's constantly changing, it undergoes just constant periodic change. And if we would be able to capture some of these periodicities already, we could probably make some of the models, whether be it for navigation, be it for planning, whatever it may be, actually more adaptive to the current state of the world. So that could be all sorts of different things we want to look at. That could be seasonal changes, right, when things grow and then disappear, weather, temperature, whatever, and often undergoes on the kind of longer-term scale, periodic changes. Down here is the video. That's the one. Oops, where are we? There are we. This one down here is actually from a 3D point cloud. This is a voxel representation of our office space, again, accrued over long periods of time, and basically there's appearance, some of these voxels are occupied, and then they're not occupied, then they're occupied, and then they're not occupied again. That's just because people show up in the office and don't show up in the office, right? They come in, they work, they disappear again. One guy up here at the top, right? That person has been there the entire night. Has been working. And so that's a way to kind of capture this, and then we try to actually turn this into some periodic functions. So to then be able to predict what changes, because how can you deal with change? Well, if you can predict change, then that's easy to handle. This is one of the first simple ways in the same office space where we had this robot regularly going autonomously on a patrol run and taking photos of different areas. Just went off every half an hour for 1 week and took a look at what the world looked like. And I don't know, was it 8, 9 places or so? Just went around. And in this case, we were trying to use some visual localization. So no LiDAR, we just used these images to find some distinctive features and use those distinctive features for the robot to identify where it was. So basically doing visual place recognition, if you want. And as you can probably anticipate, which you will see in a second, once we speed this all up, it all does this autonomously. It autonomously docks, and then it does another run. And there's a big thing to be made, I think, in robotics, that robots are perfect data gatherers. So when we want to do machine learning, we often use them just as the sort of data gathering platforms that do the data recording for us. And here's some sort of I think it was brief features that we used in this. Okay, so you did some vision processing on here, went around day and night, and always looked for features that it could detect. And then, once you've done that, if you want to then localize, you want to use these features. You want to predict which one is actually visible at this point of the time, because you've seen this was a massive change. The features that will be present at night are very different to the ones that are present during the day. So the general idea, which underpins a lot of the work we've done in terms of routine periodic modeling and forecasting, is all around model the state as some sort of binary 0-1 state or something in between. You can do very many different ways, and then use a good old thing that we know from signal processing. I suppose most people will know Fourier transform, right? So that's how you get a spectrum. So used actually fast Fourier transform on this and identified the most prominent spectral components. And if we can do this and we can predict what the state of the world will be like at a certain point of time, and because we've got this model, we've got this as a spectral components, then we can say, well, this is the most likely state of the world right now, and that can improve all sorts of different tasks. So different, here's some different examples of how this can, if you want, how this can look like. So what sort of frequencies are we analyzing, etc. We have a sort of measured state. We have got, in this case, some sort of probability function that we can lay over it, which is a periodic function here. And we then often also may have some outliers, right, which are not captured if we do the inverse Fourier transform back into the feature space. So, as we say, we only retain the sort of most dominant components. And that's, of course, is a feature. So how many of these features how many components do you want to actually retain? What's the order of your spectral model? So you're going to discard all the lower frequencies here, all these kind of irrelevant ones. So, and this one can actually be employed in a variety of different ways. One way, is what we've already seen up there, is basically modeling the occupancy of a voxel. Like, is this thing going to be occupied, yes or no? Or what is the likelihood of it being occupied? And the nice thing is with periodic function, you can basically do forecasting into any time into the future, right? We can just say, we have this periodicity, and we can go from what is it going to be like right now, and what is it going to be tomorrow at 7 a.m. So if I want to send the robot out at 7 a.m., I can even start planning now, basically, because it can predict what the state will look like. We'll make some errors, but we can do some predictions over this. Right, some kind of nice web interfaces to play this in many different domains and analyze all sorts of different features as they change over time. We've done the same for something like these predicate logic arguments down here. So that's similar to what we've seen with the planning systems before, where you again capture is a predicate true or not true with a spectral function. And then you change your planning knowledge, your planning state, and you can do the plans already into the future from this predicted ones. We've done it for sort of presence of humans, the sort of what sort of motion patterns they do, all the different things you can actually integrate with this general idea. So if you do this, got all these many different features, and indeed it can then predict if you want to go at a certain time. So for instance, this one, right? This is generally what it looks like. We just do whether this particular feature is there or not there. 3 features have a certain signature, so you can identify them through that. And then it learns this over time, and then eventually comes up with the probability of this particular feature being present. Yeah. And that's quite neat. So we can, if we do this for the entire season, there may be another periodic process which kind of is superimposed on that, which is that gets lighter earlier or later during the day, etc. So, and if you do that, actually you get better overall localization error. We've seen the localization error earlier on, so here's different things we can look at. So if we just do it statically, we have quite a high error rate overall, right? So we basically have done this sort of mapping at one point, and if we do use it a week later, and if we just use the static map, we have got 35% error rate. If we do 3 months later, we have 45% error rate. And if you do then the spectral components, you can actually get that error rate significantly down, right? Because you can predict what the world will look like at that particular time. And we also see some sort of initial trends here of overfitting. So you know the model order, how many spectral components you take into account. You see that somewhere down here, it starts to overfit, because it may have modeled something that is not valid in the long term. And you can also use this to predict what these point map, what these grid maps looks like. So this is similar map as we've just seen earlier on. You can use the same idea to basically predict what this map will look like. Rather than doing the filtering for static objects, we can predict the actual map at a certain point in time if we have got this long-term data again. And you can also, if you've got a topological map, you can say what's the chance of going through there. This is quite relevant in indoor environments. For instance, we may have edges that go through doors, and these edges will tell us that sometimes these doors are closed, particularly at the night they may be locked and the robot cannot go through them. And so you can learn again over time that you've tried to get this way, you failed. Well, the robot can then do replanning and find another route to get where it needs to be. That's already implemented, but because we can predict whether over time we learn how the world is changing, we can then predict whether we can go this route or not, and therefore we can immediately go the route that we are more likely to succeed around. So again, just modeling the probability of completing an action, of going from one place to another through periodic functions. Good. I'm going to skip over this in the interest of time, so we don't, because it's only very short. So, we have got the idea of basically using periodic functions for improving robot localization. Now, when we talk about robots in the wild, it's not only about worlds that change, we're also talking about finding and interacting with humans. And one of the ideas here was that due to the observation that the world or the people have undergo a lot of routines, we asked the question if we could actually take this robot out and make it somewhat useful in a care home. So this is part of the Strands project. The Strands project overall had this ambition of closing this loop of having robust, intelligent, autonomous behavior, which then, because it's reliable and it works well enough, we can achieve some long run times in these environments. So we can actually do studies by putting robots into these environments and let people interact with it without anyone there. So that was our main driver, effectively. And that gives us these opportunities that I've just indicated, right? Where we can learn just because we are there. We want to really get beyond this sort of short-term controlled experiments. We want to actually get these robots to learn from being deployed. And so we can then learn better structures. We can use these for improved performance, right? As I've just indicated. So the moment you have actually captured how the world is changing, you probably can navigate better, you achieve your goals faster, etc. So it gives you, again, hopefully better behavior. And in this care home, this is the robot that was there. This was in Vienna, in Austria. I think it used to be at least the biggest care home, at least in Vienna. And the robot was deployed in the sort of public spaces, data security challenges to go somewhere else. And it was there for an entire year and was providing a couple of services that we had co-designed with the carers in there. So total, it was, that's the periods when it was there. We had no people on site during these periods. And cumulatively, taking it all together, it was there for about a year. So, you know, there was another year 4, etc. And of course, the initial challenge was like, you know, what can this robot actually do? So you had to actually talk to the people in this care home, and we did sort of a bit of initial user requirements, because unfortunately we couldn't really do a lot of the things they wanted us to do. It was a European project. We were bound to this particular platform. They wanted, of course, something with hands that could carry patients out of beds and stuff. That's a different type of project. We didn't go in that domain. So in the end, we came to 3 applications, of which the walking group was probably the most exciting, because that came from the therapists. And that was an application where the robot would take the lead as a sort of pace setter of what they called a Nordic walking group. So that was just actually residents of that care home following a robot around while it was entertaining them with music. And it was to give them a little bit of exercise. And it was designed by the occupational therapists in that place. And for us as roboticists, the most amazing thing, of course, was once the project was over, they wanted to keep the robot to do this job. So they actually saw some value in it, which is rare to find when you just do research projects. The other part was that it was a sort of bell bot, so you could ask it, you know, because there's a lot of visitors, they could be asked to be guided to certain places. And the final one was a so-called info terminal. That was quite simple, basically a tablet on wheels, where the robot would just provide information on its display that people could use. So there was, you know, menus and weather and news and photos from events and this sort of stuff. So that was a bit of an artificial one, but scientifically it's provided us with a quite interesting opportunity. So this was, you know, when you could have been guided around. And this is some images from the walking group, where you see there's the therapists basically having this lanyard that the robot could see, so some fiducial markers there, which allowed them to invoke the sort of admin interface. And this was what the robot also made sure that it wouldn't run too far away from the therapists. Yeah. That was quite exciting from an HRI perspective, and there's some publications on the sort of impact of this deployment of robots in occupational therapy. Here you see some people interacting with this info terminal, where they looked at some photos. And the key, if you make it very, very simple, this whole info terminal question for us was, can we make the robot better by learning on the job? That you will see that theme coming through a number of times, because that's what I'm really excited about. Can we make sure that it is in the right place where it is most useful? So, very simple machine learning task. Again, we have a robot. We know we can localize it. We've talked about that. We know where it is. It's in this topological map. It has these different stars here. You can see them here. And it's going to be offering its services at these dedicated positions. We had to define some fixed positions because they wanted us to not have the robot go stand everywhere. And then we knew whether people were interacting with it, right? If somebody clicked on it, it was useful. If nobody would interact with it, it was probably not useful. So we defined the success as somebody interacting with it. Quite simple. So we have a location, we have a time, and we want to predict this, the probability of success, the probability of somebody interacting. Quite simple, yeah? And we used the same model, as simple as that, right? We again predicted for each of those places what is the chance of people actually being interested in this robot. And so you find and discovered quite some interesting, again, you know, it was all done on site, nobody really controlled it, the robot was there, and we just had it learn over a long period of time. And we had this relatively fast-paced main, I'm just showing the main periodic components here, at the cafeteria, right? So the cafeteria, of course, serves meals at certain times of day. If you look at it, it actually turns out it was popular at breakfast time, lunch time, afternoon tea, right? So that's the sort of dominant periodicity in that one. Then you had these things, which was interesting, that at the kindergarten, the dominant processes here were that it was only that people only interacted in the morning. We've only seen this data. Then we asked them about it, and they told us, yeah, it's only open in the morning. It closes at 1 o'clock. So it has recovered this sort of information on its own. We didn't model that. And then, of course, the big dilemma in general in computer science, whenever you do this, is the so-called exploration-exploitation ratio, right? So if you want to learn something on the job, problem is, do you completely trust your current model? Do you exploit your current model? In which case, you're doing something that is, at that point, probably optimal, but you never learn anything new, right? Because you never challenge your belief. Or do you explore? If you can go random, you'll probably learn the most, but at the same time, you're not being useful, right? You're just learning. So this dilemma is a very interesting general principle of how you actually embed long-term learning into actually deployed systems. So there's always some sort of trade-off between exploration and exploitation. In this paper, it was super boring, you know, weight of 50% exploration versus exploitation. So we just kind of used the predicted utility of a location, and then we added some randomness to it. So, and they were very simple utilities, sample to the next location to get greedily, and we went every 10 minutes, we sampled a new place that was considered the best or the random one according to our exploration-exploitation ratio. There's another paper that has done an in-depth analysis of whether you want to explore or exploit in this sort of domain, because you can actually do better than just 0.5 and see how it goes over time when you have more information. When as your model is advancing, you may want to exploit more. Turns out, actually, it was quite interesting overall when you did this analysis. The most successful points were at the lifts, so that's the color coding here. That's probably no surprise. That's where people were mostly using this robot, because that's where they hang out and hadn't anything else to do other than waiting for the lift. And if it was there, then why not just press a button? Opportunistic behavior. Most interactions happened at the kindergarten. That's because it's bigger. Kids just pressing buttons all the time. And it also has learned, and this is quite important also when you have these robots deployed on their own, this one was very, very little, and the robot stopped basically going there, and that was because the people in the care home had actually blocked off the area where it was working, and it's basically so that they put some bushes there, so it was basically impossible to reach. And so over time, the robot stopped going to these places. Right? It's very nice adaptive behavior if you want to deploy them for long periods of time. Good. This is the most important graph for us. Very noisy data, like it's the sort of the infoterminal success rate. So these crosses are the actual successes averaged over the day of the year at that time. And what we have shown here is that there is a general increase, a linear fit that is an overall upwards trend. So the robot became more useful over the long period of time in a sort of statistically significant way. And that's really exciting for any people who do some sort of human-robot interaction, because normally you've got the exact opposite. The longer a robot is in an environment, the less it's used. Right? If people are not forced due to job, etc., because you've got a novelty effect, people are very curious at the beginning and playing with it, and then over time it fades off. So here, that kind of beat the novelty effect. And it turns out that it at least became more useful. However, when you define whether a robot is useful, that just displays some information, you know, but the general principle was what we were interested in. Cool, so that's some sort of learning we can do on the job. That theme continues, so similar type of robot. So you see we moved away from agriculture quite a bit and went into the sort of social robotics domain now. And this is probably the longest deployed, so let's say interactive robot that learns on the job at the moment. This started in 2018. It was disrupted by some unfortunate pandemic. But it had carried on, and the guy on the left has done his PhD on it and has completed this relatively recently. Somewhat similar, right? Not care home. This is in the Archaeological Museum in Lincoln. It's called the collection, and what this robot is a tour guide. So we're just taking the basic system that we've done in the care home and taking it a little further. So what this robot does there, it can go around, people can approach it, they can select different themed tours that they want to go through, and then the robot will take them around. There's a bit of text-to-speech, there is all the sort of navigation, also navigation in the presence of humans integrated, all the different bits come together, and it looks quite similar in the terms of ROS systems that you have seen earlier. So we take the different building blocks and put them together to make this system work. And you know, again, as I say, similar overall approach as you've already seen. So what's the interesting part here? Of course, the sort of same, well, where could it go to best welcome visitors? So we could have done the same sort of learning in here. But what we wanted to do again is see whether it can get better as a tour guide. Right? The initial tour was defined by the educational team of the museum. They said, oh yeah, this is an interesting tour, and this is what you should tell the visitors about. So what we basically wanted to do is sort of reinforcement learning on the long term in a completely uncontrolled public domain. Right? People know reinforcement learning? I suppose so, right? So your general principle of reinforcement learning is you have a state space, which again, similar to what we've all seen in the other planning, where I've shown you where we do like AI-based planning. We characterize what the world looks like right now. We have an action space, so we can choose what we want to do given this particular state. We call that a policy, right? The mapping of the current state into what should be the next action. So in that sense, reinforcement learning is simpler than this sort of AI plan, where we make an entire plan initially. A policy is basically just modeling where we are right now and what should be the next step. And then we hope to achieve, to get to a different state that we may want to get to. And reinforcement learning is all about learning this policy, right? This mapping of state into action space based on some reward, based on some feedback, as simple as that. And yes, the main question was, can we learn better tours through some long-term interaction with the public? So what do we need for reinforcement learning? That we need to somehow describe our current state, and we need to somehow define our reward. And anyone who's done reinforcement learning probably knows that's the actual tricky bit, right? Defining your reward properly, defining how you actually give feedback to the robot to learn from, like positive reward, praise, or actually negative reward, some punishment in there. And yes, there's a lot of work these days on deep reinforcement learning, where you basically try to learn this mapping from the states to actions through some rather complicated functions, and you embed more and more complicated states. Good. So the first part, therefore, we had to answer was, what could we possibly use as feedback? We didn't want to go that people go and fill questionnaires, right? The whole point is this robot is there, nobody of us is there, we trust it can do its job. It could possibly ask them at the end of the tour, did you like this? Give me a score from 0 to 5. We know already this is not going to work, and people do all sorts of crazy stuff when there's a robot in the wild. They will just kind of press random buttons. Half of it is kids, they probably won't understand what this is all about. So we ruled that one out. Thought like, well, we should be able, as I'm standing here and I just look at your faces, I can probably see whether you are still paying attention, right? Or whether you're doing something else. So the question is there some sort of engagement from people, or is there not? And if there is not, maybe that's a negative reward. And if they are still engaged, maybe that is good, right, for a tour guide to say, carry on. So we did some end-to-end learning, really simple from video frames. Robot has a camera, looks at these participants of any tour it has, and again, do something as simple as that with a bit of time series analysis using an LSTM here on a regression of what is basically an engagement value. Now here comes one of the challenges. How do we get the data for that? So we needed to get somebody to actually tell us what engagement looks like. And there's huge body of literature in cognitive psychology, etc., on how you can measure engagement, right? So you do things about gaze and shared attention, and all these sort of bits are in there. Well, we thought, well, actually, people have a quite intuitive understanding of that. They may not always be able to describe this, but if I look around, I can probably see who is currently doing their email and who is fully listening. So I can intuitively do that. So we assume people can also do that, and all we did is basically we did all these recordings, gave it to a bunch of people, and they watched them actually at higher speed even, and they gave just a very crude, they were given a slider. They could just basically watch these videos and constantly say, oh, well, these people seem to be paying attention. Oh, no, they're not. Oh, yeah, they're paying attention. Oh, they're not. And we gave this to a couple of people. And surprisingly, the inter-rater agreement between the humans that did this annotation was quite high. So they actually seem to have an intuitive understanding of what it means that people are engaged when they are looking at the robot and when they are following around and looking at the things that is referring to, etc. So really just a video study, people annotated this, learned it all the way through, and then you probably can just about make out this line here. So, that gives you an indication. So now they are coming back, they're looking at it, it's like a high engagement, they're listening attentively, they're looking at the things that are referred to. When they disappear, it goes further down, etc. So it's noisy, right? It's really noisy feedback. But there is some feedback that we can use. And that is all we need, really, for reinforcement learning. So every day, the robot would go out, do these sort of tours, measure its engagements. At the night, we do this sort of a batch task. So every night, it would process the data it had gathered and retrain its policy. And this is quite complicated to fully understand. I'm not going to attempt to show it, but it gives you an indication of what this policy looked like. So it has learned that if there is high level of engagement, to describe more and regularly to just tell people more and kind of go to another exhibit and change the order actually slightly around when they were less interested. So you actually learned different routes. So this shows just different pathways through the policy based on the current state, the state then being things like the current place, the past of the history, the things we've already seen, etc., etc. So we can basically always decide which is the next exhibit and how much should I talk about this. And indeed, similar sort of linear fit graphs as in the previous papers. Here's the initial period where it didn't learn anything. So over time, the interest went down, or the sort of engagement went down. Then, after some period of time where we had this sort of system enabled, so this is kind of averaged over the entire weeks, I believe. It consistently went up, and we said, oh, this is just a sort of artifact of this. So we turned it back off, and it dropped right back down. So we went back to the original tours. So that actually it learned just from being in these environments. So this is a sort of first initial data gathering period. This was when it was consistently learning, and then we kind of went back to the baseline model to see whether there's a temporal inconsistency. And yes, excellent. This robot got better at giving tours. Cool. So let me just see. I've got half an hour roughly. So that was 2 examples of robots getting better on the job, right? Actually being immersed in an environment and using the experience it gathers over time to get better on this job, either by exploiting this periodicity or by actually doing typical reinforcement learning based on some feedback. That's probably 2 of the ways you can use this. Other thing about long-term stability and reliability of long-term deployment. So what's important for this to work, right? That we can actually happily say, are we going to stay away from this? As I said, autonomous systems in the wild, I want them to be completely on their own. I want to leave them in there. So what's important for that? And this comes back a little bit to the sort of overall architectures that I showed at the beginning, right? So sort of you will remember that we talked about deliberative architectures. There's a sort of planning deliberative part at the top, and then there's lower level execution of different skills, which are often in these sort of ROS systems, individual components. So we have a localization and navigation system that has a sort of continuous space representation. We always build on top this sort of topological layer, which you have seen that can come from some sort of graph SLAM methods, or you can handcraft it. So that's how you introduce some sort of discretization of space that you can do some reasoning about. And all actions are basically then things like, oh yeah, I want to somebody tells me I need to go from this place to this place, so you do some route planning of how you get there. We can model the probability of success of traversing such an edge, for instance, with these periodicities as we've seen before. So for instance, it may tell us that this edge at a certain time is very unlikely to succeed, so the robot could actually go directly along this edge, which would lead it around this part, right? So that's a sort of topological layer on top of that. On that, we need to do quite some monitoring and see when errors are happening. Monitoring in that sense that feeds into this sort of learning potentially, but also to invoke recovery behaviors. And there's different recovery behaviors that one can implement. So we can just quite often, as it is in robotics, why, just wait a second and try again. Maybe the world has changed. We also had a backtrack behavior. Sometimes the robot would get itself into a sort of strange situation. Just retrace your steps where you're pretty sure that was safe, that you came, and then try again. Or actually request help, which is a very important feature. We have this sort of executive control on top of that, which then allowed also to identify when we had to do completely replanning, etc. And then there was this sort of higher level that defined these tasks. So what I'm going to talk about is the sort of special methods in this navigation, right? So here is an idea from a long-term deployment this is in Milton Keynes, in an office space where this robot was running around. And we were looking at the sort of navigation failures that happened. Like when did the robot do any sort of recovery? When did it do backtrack? When did it sleep and retry? And how often did it work? And how often was it successful and unsuccessful? That's what this graph shows. What is this? All right, there we are again. And then we had sort of special behaviors like the one that you've just seen on the bottom right is the sort of door passing behavior, and other special ones like autonomous docking, etc. So here's one. Robot doesn't have any arms. In this environment, robot stood there, couldn't go through the door, had to wait for some human to do it, and people are willing to help to some extent, right? They do this. They accept this sort of, when the form factor of the robot gives it away, and it is clear that it can't do that job, then they are happy to help it out. Sometimes they're a bit impatient. Why does it take so long? But it can detect that doors are closed, and it can also, even at this point, for instance, we can again learn over time the success of being helped. So that then determines whether the robot will decide to go through this door and wait for a human to help, or whether it will go all the way around, because there was another route to get to the other side of this office building, but it was about, 300 meters through the rest of the office. So you can weigh off these differences here. And down here at the bottom, you see all the requests in this care home. So this is the same map that you've seen before, where the robot was asking for help because something's gone wrong. And something always goes wrong. I'm going to talk a little bit more what can go wrong. But this is where it was asking for help. And asking for help is fine in principle, because sometimes people do help, but most often they don't, and you just have to wait, right? So you see the sort of blue ones is, these are the edge numbers of how frequently errors along these topological edges happened, and we've just ordered them in, what is it called, decreasing frequency of how often errors happened. Here's something that clearly, there's one edge where errors happen very regularly, and then it got some help, and some other things happened, errors happened quite regularly, but help was hardly ever available. So help in this case was, a person helped out. And what we did in this paper is, because the whole idea is, it's fine to fail if you go out in these environments. People will accept that. People help. What they don't accept is that you make the same mistake all over again and again and again. Right? So particular, we have, for instance, in this care home, if there was one edge that was particularly difficult because people consistently put stuff there, right? They put something in the way. The delivery man came and put some boxes in this area, etc. And there's always the old poor guy who worked at the reception, and constantly the robot would, very regularly, it would fail in this particular place, and it would ask, "Sorry, I cannot move right now. Can you please and help me out?" And he found that funny, first 2 occasions. Then he found it acceptable, next 2 occasions. And then he wrote an angry email. It does this again and again. It's so annoying. Can't you fix it? So at that time, we had to fix it manually by moving the edge. Blah, blah, blah. But that can't be a solution. So that gave rise to this idea of, well, we need to learn from these demonstrations. The demonstrations in this case was that people were asked to help. We disengaged the brakes, and they were encouraged to actually push the robot a little bit out of the way, out of this situation, and then carry on. Again, that's an opportunity to learn in the wild, right? So initially, we just disengaged the brakes, and people moved out of the way, and then it just tried to carry on doing its job. But we didn't learn from that. So then we started like, oh, actually, we can learn from this. So let's have a look rather if we can use some Gaussian processes to model these demonstrated trajectory. So these Gaussian processes are quite typical way of doing learning from demonstration. So you basically give lots of demonstration trajectories. Normally it's done in sort of manipulation tasks, for instance. We took that into this navigation task, right? You have a sort of, again, your laser provides you with this sort of state description, so you can assess the situation, and then you see the demonstration as you see this sort of pushing as a demonstrated trajectory. And then you try to actually invoke this recovery, invoke this sort of learned trajectory yourself to get out of that situation, to avoid getting into the same trouble again. So it's a sort of additional recovery behavior that is learned on the job by using Gaussian processes to model these trajectories. It still isn't easy, right? So things go terribly wrong sometimes. Everything is pretty much built on a large bunch of off-the-shelf ROS components, so they are, still research software, but of decent quality in many cases, let's say. Then you still have terrible things happening, like this is actually the robot has fallen down the stairs in the scare home. Why? Because human error, somebody decided to disable the cliff detection. So I had a kind of Kinect looking down to see obstacles in front of it and also see cliffs. And some guy in the team had at some point decided, it's because it had a number of false positives and when will we ever encounter stairs? It hardly goes anywhere to stairs. And of course, it did. Right? This was disabled for a week or roughly, and it took us much longer to recover from that because obviously the health and safety person in the care home was not very pleased with this situation. So to regain their trust was a particularly difficult one. So we also spent a lot of time to actually establish the proper CI procedures for robotics. So lots of software engineering and robotics goes in there. So a lot of people of you will know general principles of continuous integration. The only difference really with robotics is that you really often have to do full systems testing. Right? We don't have so much unit tests often. I mean, each component can and should be unit tested, but we do a lot of more systems testing. So this is just a short video in this particular setup where a lot of our ROS test cases are automatically deployed on our Jenkins server and basically are running simulation test cases. So similar to what I've given to you, right, a nice Docker container, which is sort of simulated environment. We run these through in a sort of relatively lean way, define, for instance, navigation test cases, and every change to the overall system goes through those before it is being merged in there. So there's quite a nice sort of framework of how you actually define these test cases as navigation scenarios, for instance. And then you can inspect them straight away. And this is also then often done in a sort of testing hardware in the loop kind of way, if you want, right? So we can flick a switch that rather than testing this in simulation, we can say, well, this particular pull request should also be tested in reality. That is, of course, done under some human supervision. So this used to be our sort of simple test arena to have this robot up and running there. And so I could actually at that point tell the system, right, deploy this test case or deploy this pull request on our real robot, and people observed that. But somebody had to then basically accept it and go over and have a look at it, and then eventually said, oh, well, okay, no, robot moved as expected. That was quite essential to get to the level of robustness to allow these robots to run for a year. in these environments. Good. So I think the key message that I wanted to tell you about is then here, one of the key things in robotics and for long-term autonomy is that we want to embrace change, right? So we have things, how the environment changes, we want to model that. It is a challenge, but at the same time, it is also an opportunity to learn more. Right? That's why, for me, it becomes very interesting. We can get through these changes novel ideas of what we want to actually put our research on. And indeed, interaction with humans, while difficult, also provides a rich set of inputs to learn on the job and get better. Generally, this is anyone who does robotics, it does fail. This is not, in that sense, an exact science. So we need to be smart of recovering from failure. And I think another part that I haven't really talked much about yet here is how we can detect that things are not quite working out. So many different things can go wrong. I think I forgot whom I talked to about, but we talked about detection of cyber threats, right? By basically doing machine learning and learning certain patterns of the correct behavior of a system, and then seeing whether you are having a cybersecurity threat by seeing that you have a deviation from your learned model. We do the same in robotics. Right? We basically done some work on simple anomaly detection where we use like a one-class SVM, where you constantly use the robot when it is operating correctly. In hindsight, you know that this was a good day, it was running all fine. You can feed that in there and say, like, this is the correct behavior, because you try not to model all things that could possibly go wrong. You just try to classify this is correct, and then you have an indication of when things may go wrong. And that's also particularly important with the robots here in agriculture. So this is, again, the Saga robotics platform. This is a company that is now providing crop care as a commercial service. Initially, when we started working with them, these robots had about, I would say, probably about 100-meter mean distance between intervention. Right, that's the metric that we are particularly interested in long-term autonomy when we go out in agriculture. It's the typical metric that we use is mean distance between interventions, like as the sort of mean failure or average time to failure that for hardware testing, etc.
Why not median?
Why not median? Yeah, why not? Good question. Do you prefer median? I haven't thought about it. Do you want median?
You know this joke, how to become a millionaire. You go to a football stadium and enters Bill Gates, and now everybody is a millionaire on average.
Okay, right. Yeah, good point. I've not thought about it. It's one of the kind of typical things. It's what people do, right? Whether you want, because you want to have it to be somewhat sensitive to the outliers, right? What a mean does. So if you have got, a really bad case, you want it to be reflected. You wouldn't have that with a median. In the end, you probably want something like, I don't know. We should look at the distribution correctly. Can't tell you which is the more accurate one. But what people normally do is the sort of average time to failure, right? And we often look at, when we talk about navigation, about the mean distance or the average distance between failures or between required interventions. And now it's basically, but now they can do several kilometers, right, without any intervention. Intervention means, the robot also doesn't just crash into something, but it flags up that it may have some problem navigating autonomously at this point. And I think for that you need to kind of also, we've done quite a lot of more adaptation on the job. Often I don't know if anyone has done and tried to make robotic systems, navigation systems work. There's a whole ton of parameters that you can optimize. Lots of meta parameters that turn out to be actually quite important. Making this all manually is quite annoying. So there have been some work also on using machine learning, genetic algorithms, etc., to try out and optimize these parameters in a sort of learned way. Meta-parameter learning is quite important to increase the reliability of such systems, etc. And I hope I also convinced you that sort of routines just give you only, because the nice thing about routines periodic models is they require very few parameters. You don't need huge amounts of data to start learning some periodicities, right? And so that's often easier than to try to learn complete time series models, which may be richer, but they are actually quite hungry for data to provide you any meaningful input. Good. Last little bit of entertainment, let's say. When you take these robots out into the world, into the real world, the worst thing that you encounter is humans. This is an image here of a lady, and you just see the finger there. This finger has just been lifted off the emergency button. So, of course, every robot these days needs an emergency stop button, and it needs to be clearly visible and quite obvious, which of course means there's a strong affordance to press it. A red button, why not pushing it? In particular, when you go into museums where you've got kids around that don't necessarily understand yet what emergency stop means. It's a button to press. So on average, that happens around twice a day. So one of the most important recovery behaviors was that, my emergency button has been pressed. Please assess the situation, and if you think I'm fine to carry on, please release it. So it's a very important feature in here, and because it happens so often in this care home that we eventually started grabbing these snapshots, right? Whenever it was pushed automatically, the robot took a photo and sent it to us on Slack so I could see, oh God, again. And who is this? So we found then over time who are the main culprits who just constantly do this. This is work from folks in Japan. You may know this video. I found it. So they had a robot deployed in a shopping mall, and it did similar things, like it guided people to shops, or kind of a typical scenario that is often being used. And then kids, right, found this robot and started playfully with it. Yeah, that's all very nice. Then they were a bit more brutal. And you won't believe how often I had this problem that sensors needed recalibration. Like people kind of forcefully twisted and played around with it. We had things of robot not being able to move in the museum because it had something that was an obstacle in its laser scan. We can see remotely, we can look in on, like, oh, there's something that's really close. What is there? Turns out somebody had wedged a half-eaten sandwich into the slot where the LiDAR scanner sits. I have no idea why. Here is another example that stopped the robot from charging. Again, when we deployed this, we had them, at that time we had Slack, and anything that it encountered gave a notification on the phone. Here it was going to dock to charge, and what you see down there, so there's these two copper contacts, that's one, that's the other, and this is a pink chewing gum that it had mopped up from the floor somewhere. And I can tell you chewing gum is not very conductive. So overall, in general, when you have this, falling down the stairs, human error happens all the time. People changing the environment in ways you didn't anticipate. So this was another incident. So you don't see it down here, but behind this little chair is the robot's charging station. So somebody decided to put a chair right over it. And the robot told us, oh, docking action has failed. And luckily, we had a sort of, photo of it, how it happened. Then they decided to, the graph here shows again the sort of number of navigation failures on certain days. And so this is, some days are very, very nice, and some days there's just plenty of them. And of course, this is not, when they shoot up here, this is then trying the same again, until we finally sorted it out. So that's why this shows up so much, right? So here Here they put on a Christmas market in this care home. Didn't tell us about this. They just actually, what they've done in that case was they were decorating something, and I don't quite know why, but they were handling with paint, so they put some sort of cover sheet on the floor, this very thin plasticky stuff. So, and that was invisible. The robot came in and kind of nicely wrapped it around its wheels while it was carrying along, and then couldn't move at all anymore. Charging station block, sofas on sort of waypoints, moving stuff around. We can cope with some changes, as you've seen, right? When the map changes, and kind of react to that, and sometimes even the robot will just fail. Happens as well. Good. Okay, I thought that is probably enough for now. If you want me to carry on, I can tell you a bit more about agriculture, because yesterday it failed to ask you what you wanted, because then nobody put the URL on. So I've just taken the liberty to talk about what I thought you might be interested in. But if you want to talk about something a bit more, we have the opportunity. I may have a few slides that we can still whip out. Otherwise, thank you so far. And I put all the materials there. I'm sure we're linking that from the official school as well. So, but you can already have a look at slides and other materials there. And if you want to do your homework still, feel free to do. Thank you.
A question about in one of the examples you showed how to build maps over long term, and then ignore the things that appear and disappear.
Yeah.
And then what you said towards the end of it, then you can actually take that trained model and embed it as a filter directly, for example, for the LiDAR. Now, how do you update that model? Or how often would that kind of filter need updating and to keep up with the changing environment?
Okay, so I think when I say you can use that model to implement a filter, it's not that model, right? We are basically learning a filter with this similar idea, similar auto-labeling of having different timed maps, but basically extracting from the different timed maps virtual scans, and then learning a filter based on those scans from this automatic labeling. So basically we want to get rid of the idea basically of getting rid of the automatic labeling and using temporal maps as the auto-label process. That's the same idea. What this filter then learns is not the specifics of that map and how it changes. What it learns is basically the geometric structures that are considered stable or unstable. So for instance, without doing explicit semantic segmentation, so without saying, oh, this is a tree, and a tree is, in our view, stable, or this is a car, and this is, in our view, unstable, it does basically an implicit segmentation of the scene. Right? So basically what comes out, if you then put any sort of scan in there, you will find that cars, because of their shape, so they're basically segmented, so you get a segmentation out of that thing, are considered unstable. Right? So we don't explicitly represent them as a segmented entity, but all the points that actually fall onto a car because of the neighborhood and the geometric structure around them, these points will be labeled as very unreliable, while points that fall onto some vertical poles and flat walls, for instance, quite extensive walls, from this learned system actually are usually characterized as fairly stable, because that's what the data has told us. So as long as this doesn't, so you need to train this basically in that domain, right? So when there is trees, it will work in similar domains. When there is cars, it will work, but you don't train this for different time periods as such. You use just the temporal aspect you use as the auto-labeling feature. So you basically the stacked maps and time-stacked maps you use as the way to get your labels to then train this segmentation or this filter on.
And does this actually apply also to agricultural settings.
Yeah, absolutely.
When
So
you have
because in
changing-
the agricultural thing, so in that paper we've done it in this I can probably just quickly dig this out. I don't know if I go here, ESSCaSS BLT. So this is the data set this is being used on. And you get this sort of real world, and this, the one I've shown you is the sort of simulation of that sort of domain, right? So you've got this long-term data set. This is what a vineyard looks like in March. This is what a vineyard looks like in June. And we kind of run this around this vineyard autonomously for a couple of, several recording sessions, gathered all the data. And what this filter then learns is that these vertical poles actually are quite useful, and they are not specific to this particular domain, right? It is then a generic filter, and we've taken this, and in the paper we've done this from, which was trained on this particular vineyard and taken it into a completely different vineyard actually in England. We have wine, you won't believe it, right? And it does that domain transfer quite well because these are structures that are generally there, and also you can't see this here in the map, just about in this area, there is a building, and here's another building, right, which has nice flat walls. They also come out as stable features. And so basically the detector now does not just recognize a house or a stable a wall in this particular environment. In generally, it will consider flat walls like this as stable features. Now, problem, for instance, we did not have any, I don't know, cars, lorries, big trucks in that, which also have nice flat features, for instance, right? It would clearly misjudge those because they were not part of the training set. Yeah, but it's not specific to that environment. It is then a filter that generally provides basically an assessment of the likelihood that a point in a scan is part of a stable element or not. Yeah.
So in your talk, you mostly focus on long-term things which changes over like hours or days. But in these deployments, like in museums and office spaces or even like hospitals, how much challenge was to counter changes which happens like within seconds, like the fast changing stuff, like crowds and localization failure because of the crowd stuff. Like there are a lot of crowds and the robot perception is completely blocked, or it cannot navigate because there are a lot of people moving very quickly.
Yeah. So indeed, so you're right. So for instance, so this is the short-term change, the typical one, let's say there are crowds of people gathering around a robot, blocking it. And in the museum, you have that's all the time, right? So that, so indeed, what happens, we haven't looked much at it, but you've seen some of the localization examples. So what happens when you often have these sort of crowds around this and you do localization and these particles spread out, they disperse completely. There's some automatic monitoring for that. So we basically monitor the covariance of this particle cloud effectively, and it will stop, and similar sort of things happen, like a recovery behavior kicks in, right? If you're really unsure about this situation, then before moving, and because you're unsure where you are, you ask again for somebody to help you out, potentially in these situations. So I skipped over this sort of navigating in crowds, because the other thing we've done, and you find this when I can, if we have a quick chance to go back there, I'll do it. Because it's maybe a good point to have a, hang on.
These are handled well by your ROS off-the-shelf stuff.
Okay, so hang on. I'll just split. Do you mean the sort of localization losses and stuff?
Yeah,
Or?
even the so the ROS, like in your slide, like one of the things you mentioned, like most of the things are built on like off-the-shelf ROS.
Yeah, many are.
Navigation step, base. So are those powerful enough to handle at the moment like fast-changing dynamics?
No, as simple as that. No. When I say it's largely built on this, of course, you know these systems are built of 100 components, and of maybe 10 of those, or maybe 20 of those, are basically our own research components, right? That's the rest is just off the shelf, nice bits and pieces that you put in. So for the navigation in the presence of humans, for instance, when you've got crowds, the off-the-shelf stuff doesn't work. Let's be very clear about this. And that's why, you know, we actually had a lot of research projects on human-aware navigation. And that still is happening at the moment. And the biggest challenge that you've got with, we haven't seen this much, but the biggest challenge you've got often in when you want to navigate around people is that this robot is constantly replanning in the presence of obstacles. So, you know, you've got a person standing here, robot plans to go this way, sensors models, you know, send its data is a bit noisy, or the person moves ever so slightly, robot decides to go left again, goes right, goes left again, or doesn't move at all because there's just not enough space in there. So that's where you need to model it in different ways, where you need to actually really focus on navigation models in the presence of humans. One thing we have done here is basically achieving some commitments by, that's why I was trying to quickly look at that example. If I finding it, yes. Let's look at this very quickly. So that you actually not take humans as the normal obstacles. You first do some people detection and tracking. So use multiple sensor fusion to actually do this and to assess their trajectories. And then you can use something what's called a qualitative trajectory calculus, which discretizes in simple ways, again, the general movement between 2 points in space, in 2D space. Sounds quite strange in some ways, adopted actually from geography. They use this sort of qualitative trajectory calculus a lot when they define how things are moving in space in relation to one another. Without going into too much detail here, what it allows you to do is that you have a sort of every interaction between a human and a robot goes through a sequence of these states, right? You may first approach one another, then somebody veers to the right, then you carry on, and then you basically pass each other. So when you encounter, and you've got these encounters between human and robot, it may be these kind of typical situations, either of passing on the left-hand side, passing on the right-hand side. You've got situations where you come perpendicular to one another, or where you've got one overtaking or the other. So there's a number of typical situations, and you want to model those in a way that you don't just rely on the normal navigation methods in here. And this was one approach here where we've learned this. I think is it working here? Kind of. So where we basically turned it into a Markov chain with probabilities, how likely is one state following the other. And you then get this sort of commitment trees, let's say, right? So you get this graph here. When you see that one person is moving slightly to the right, that means from now on you are most likely going through this state transition, and the robot can act accordingly. For instance, then it doesn't do this sort of waving around, but it's committing to actively go past this person by basically maintaining a state where they are kept on their left-hand side, for instance, when it is a situation that you've identified. So that's one way where you actually put a bit more context and then explicitly model this sort of situation, right? We have this, for instance, here, this is one encounter, person comes towards them, robot has now committed to keep on the right-hand side rather than trying to constantly plan around them. And that proves ways better than the sort of standard, DWA, which is part of MoveBase or some others, when you have actually situations where you encounter people. So that's one way. There's many other ways. As one of my colleagues also treats it as a game theoretic problem, right? The encounter of humans and robots with one another, where you have where you kind of bargaining, like, who's going to back off a little bit, and what's the chance of the other one basically letting me past. That's more in the context of autonomous cars.
The chicken game.
Yeah, exactly. It's a game of chicken. Exactly. So, yeah, so that needs special treatment. It does. And
okay. I see that the time is up, and another round of applause. And in dark nights of England, you can use this reflector bag to keep you safe. That's all the stuff inside.
Thank you very much. Thanks.